For inviting me to speak. Actually, about 2 years ago, almost to the day, not really to almost to the day, almost to the month. So I gave a talk at ICMS that where I proposed this problem that I'm going to tell you the answer to today. So it's taking me some time, but I thought this would be an appropriate place to give a talk about this. So let me start with an example. So I'm going to be working on a 1D spin chain. So the quasi-local algebra is the tensor product, and actually, my example, it'll be a 2x2 matrices, so I have qubits living along the line. And I'm going to consider one of everyone's favorite Hamiltonians, the transverse field Ising. So sum of sigma I z sigma I plus 1 z minus h sum sigma I x. Okay, so this is a transverse field Ising model. J and H are just some parameters, okay? And what is this? This is Pauli, in case you're not familiar with the lingo, sigma z is the Pauli z operator, and sigma x is the bit flip. And then the subscript I just means it's acting on the ith site of the lattice, right? This is summing over all things in Z. And so this is a really famous example, in part because we understand the solutions. But one of the most interesting properties about this is that it's symmetric under the standard Z2 action. So there's a canonical Z2 action, the bit flip action, namely on each site, it's given by sigma x. You switch 0 and 1, and you can kind of apply it diagonally and conjugate by it. So there's a Z2 action. I can think of it as acting by automorphisms on my quasi-local algebra by sending the non-trivial element in Z2 to the automorphism, which is basically add of the tensor product of sigma I x's, right? So I'm just conjugating by the diagonal bit flip action. And the point is that this Hamiltonian is symmetric under this action. In fact, each of the terms are symmetric, so it's nice and locally symmetric. And so this is an example for different values of these parameters. I have different Hamiltonians. These are examples of symmetric phases in the sense roughly that Yoshiko was talking about yesterday. In fact, when so let me say this is symmetric. And there's two different kind of regimes. One of the regimes is when J is much smaller than H, and the other one is when J is much larger than H. In these two cases, the systems are topological in a certain sense. They're examples of SPTs. Well, in a slightly more general sense than maybe people have been talking about it before, but they're very different SPTs. So in this regime, there is a unique symmetric ground state, and it's just a product state, an infinite product state of symmetric ground states, right? You take like 0 plus 1, divide by square root of 2, and take the infinite product of that, at least when J is 0, and then there's a formula for what it looks like for other values here. But here, it's what's called a symmetry breaking state. It's the unique symmetric ground state of this Hamiltonian is a mixture, a convex mixture of two pure states, neither of which is symmetric. It's the tensor product of all zeros and the tensor product of all ones, and you take a mixture of those two. So these are both symmetric phases, but they're very different. And when J equals H, when you get into the middle, there's a phase transition. This is a famous phase transition where the universality class is supposed to be described by Ising CFT, right? So one thing that's super interesting is that there's actually a way to relate these two very different looking phases that actually tells you something about the critical point at J equals H. And that's called Kramers-Wannier duality. So let me explain how I think about Kramers-Wannier duality. And the way that I do this is I can take the symmetric subalgebra. So this is just the subalgebra of quasi-local operators that are invariant under the Z2 symmetry. And it turns out that this is generated by the terms of this Hamiltonian. So if I take these operators, sigma iz and sigma ix, and take the C star subalgebra of the whole quasi-local algebra generated by them, it generates the symmetric things. And what I can do is define an automorphism on this symmetric subalgebra called beta. So beta, I'm going to define it. It's going to go from B to B, defined by beta of, so I'll define it on these generators for you. I'm going to send this to sigma I minus 1 x, and beta of sigma I x goes to sigma I z plus 1. And so the idea is that it exchanges these two types of generators, but there's a little half shift that goes on. So if I do this automorphism twice, I just get kind of a translation going on here. Okay, so this is actually an automorphism of this algebra that has bounded spread. So this is what's called a bounded spread automorphism, and this is an important component of the talk. What does it mean for an automorphism to have bounded spread? It just means that if I apply this to BI, which BI in this case is just this subalgebra B intersected with the operators localized in an interval I. So this is just the symmetric local operators. This is contained in BI plus R for some R. What is BI plus R? So this is a little bit confusing notation. You might think since we're working in a group Z, I plus R means translate I mean take an R thickening of I. So you add R to both ends of I. So it's a little bit bigger interval. It's an R thickening. And in this case, I can just pick R to be 1 because it just does kind of like a little half shift translation. But in general, bounded spread automorphism would be some automorphism of some kind of quasi-local net of algebras over Z that satisfies this for some R. Okay, now it turns out you cannot extend this. Let me say this. You cannot extend B to a bounded spread isomorphism from A to A. Okay, that's something that you cannot do, but you can extend it to a channel on A. And the way that you do it is that there's a canonical conditional expectation from A to the symmetric subalgebra, namely just average over the group elements. So what you can do is define beta tilde to be equal to do that canonical conditional expectation and compose it with beta. And think of this as mapping from A to A. So it's a quantum channel now on the big quasi-local algebra A. But what does it do to this Hamiltonian if I take beta tilde and apply it to H, J, H? It just gives me this Hamiltonian where the parameters H and J get switched because I'm just switching the two terms and it's an infinite sum. So you don't see this shift. Okay, so actually I have a locality preserving, this bounded spread is often what people mean if you hear a physicist say locality preserving. They mean something like this bounded spread condition. You have a locality preserving quantum channel that relates these two different phases to each other, even though they look qualitatively very different. One's symmetry breaking and one's a pure state. Okay, so that's really interesting, and you can actually use that to argue that this thing is a critical point. In other words, it can't be topological. I won't get into the details of that, although there is kind of a nice way to understand what's going on there. But that's one of the reasons that this duality is really important, is it gives you a way to understand relationships between symmetric topological phases that you might not have understood otherwise. So the goal is to classify all of these things. Okay, when you have some symmetry acting on your system and you want to understand what are all the possible kind of duality channels that look like this, namely bounded spread automorphisms on the symmetric subalgebra, you just would like to have a complete list of these sort of things. Okay, what setting do you work in? Actually, most of my work, I work in the setting of categorical symmetries. So we heard in Matthew's last talk about having these non-invertible symmetries. In 1 plus 1D, the right kind of non-invertible symmetry you would have is a fusion category acting by symmetries. And there's actually a great theory for that. You can use matrix product operators, but there's even a more general thing that I worked out in my a recent paper with David Evans. But for the purposes of this talk, I'm going to restrict to group symmetries, just to keep it simple and not have to go into these details of categorical symmetry. So the setting, I'm going to have a representation of G on C to the D. I'm going to have my quasi-local algebra, my big one, to be the tensor product of these matrix algebras. And just like before, I'm going to define B to be the fixed points. Okay, and this representation should be sufficiently nice. Okay, so think something like the regular representation. The actual condition is something like, if you look at the center of the group, it should be a injective, the induced map from the, it should induce a map from the center, the group algebra of the center should be injective. But from a categorical perspective, this representation should just kind of tensor generate the whole representation category nicely. If you want to, and actually the main theorems are about the case where this is going to be the regular representation. You can just keep that one in mind, which generalizes this spin flip case. Okay, and this, you can define BI to be equal to B intersect AI as before. And you can think of this B as its own kind of net of algebras over Z on its own, right? It's its own kind of quasi-local algebra. And so the problem is to classify bounded spread isos of one of these fixed point nets of algebras. Okay, and bounded spread isomorphism, the definition is the same thing. It's an automorphism from B to itself that has this bounded spread condition. And as before, this gives you a duality channel in the big one because there's this canonical conditional expectation. You just average over the group elements, the automorphisms, and you get a conditional expectation onto the fixed point, and you can compose them to actually get a channel on the big one that does interesting stuff. Okay, so you can kind of reduce this problem of these duality channels to just these bounded spread isomorphisms on the small one, and you want to classify those. But the question is up to what? Because anyone who has spent time thinking about automorphisms of C-star algebras or things like that knows that there's way too many of them to have any kind of reasonable classification. So whenever you talk about classification of these things, you want up to some natural equivalence relation that actually makes things manageable. Yes.
So all the non-invertible symmetries that have appeared like in one-dimensional chains have this form of being like an automorphism of the invariant algebra composed with a conditional expectation.
So all the ones that appear in the literature do, but there actually are more general ones, and this is kind of like an average over those. So there always is one of these you can get from one of those, but that's another story. Yeah, all the ones in the literature do like this, but actually there's more general ones. But you can still kind of the bounded spread isomorphism part. You can classify all the extensions by channels that restrict to a fixed bounded spread isomorphism in terms of categorical data. So we can talk about that more afterwards. Yeah.
Sorry.
Yes.
So with no problem, there's no more Hamiltonian, right?
Yeah. So this is kind of I motivated this with a Hamiltonian, but yeah, there's no more Hamiltonians. There's no states even. Although it's very interesting once you understand these dualities, once you classify them, to try to understand how they interact with states and invariance of states or Hamiltonians and this sort of thing. Okay. And in particular, if you have one of these bounded spread isomorphisms and you have a Hamiltonian, you can apply your bounded spread, this duality channel to the Hamiltonian. You get some new one that it's dual to, and sometimes you get very interesting things out of it. Okay. Yes.
So in a sense, change the group. So it's easy to have many groups that give the same B.
Yes.
For example, you could have finite and then compact, and you get.
Oh yeah. So
you don't have any stability on the state.
So let G be finite.
Yes.
Yeah, but right. So this only depends on the B.
Let's say you take the von Neumann algebra generated by G and then take the unitary group of this, you get the same fixed point.
Yeah. So, and so this property only depends on the fixed point subalgebra. It doesn't really depend on G.
On G. Okay.
Yeah. Well, the fixed point subalgebra depends actually on the category, the tensor category, rep G, and the object in rep G that you have. Okay, so up to what? So there's a special class of these bounded spread automorphisms of these symmetric subalgebras that are kind of considered trivial, and these are what are called finite depth circuits. So what is a finite depth circuit? So I'll give you a kind of cartoon picture of what it is. You probably have seen, if you've ever been to a talk about kind of quantum information or something like that, you've probably seen a picture that looks kind of like this. Maybe I'll draw 3 layers just to show what I mean here. But the idea is that each one of these is a unitary, okay, and it's a local unitary. And each layer, the unitaries are disjoint from each other, but the support of them, it doesn't have to be the same, but it just should be bounded, uniformly bounded in size on each layer. And then, of course, the tensor product of these unitaries isn't an element in the C-star algebra, but conjugating by that tensor product gives you a well-defined automorphism. So that's this add. And the idea here is that I have a finite set of layers, and the key point is that the layers don't have to, like the supports of the unitaries don't agree with each other. So when I look at the spread of one of these things, there's this little light cone that appears. And so if I took some observable localized here and I conjugated by this thing, the new observable is going to be localized there. So the spread is bounded, and it's a function of the bounds on the supports of the unitaries and the number of layers you have. Okay, so there's a lot of these, right? You can just construct way too many of these sort of things. And so the idea is to try to classify these up to those. Okay, when I would like to classify, it turns out that these bounded spread isomorphisms form a subgroup. These form a normal subgroup, and so the question is, what is the quotient? So, new question: what is group? And I'm going to do something a little bit funny. Some people like this, some people don't like this. I'm going to call these bounded spread automorphisms of these things QCAs. That stands for quantum cellular automata, because if you apply this to if the symmetric subalgebra is just the whole thing, this is literally the definition of a quantum cellular automata. So this is like a quantum cellular automata defined on a symmetric subalgebra only. Okay, so I'll call it QCA of B modulo finite depth quantum circuits. So that's the question. Okay, good. Everyone happy? So when you're trying to answer a question of classifying something up to other stuff, the first thing you do is look for invariants, right? So maybe I can find homomorphisms from this group of QCA to some other group I like and know that contains finite depth circuits in the kernel. And if you find maybe enough of these or a good enough one, maybe you'll get a complete invariant for this sort of thing. So I'm going to tell you two invariants of that form, and then show your theorem that in this case, when you're using the regular representation of G acting on itself, that those are complete invariants. Okay, so in other words, if you just know the value of these two invariants, you know completely the QCA up to this equivalence relation of finite depth circuits. So the first invariant takes a lesson from local quantum field theory. So if you think of B as an independent net of algebras, okay, it has what's called a DHR category. Okay, we all know and love a DHR category. But what do I mean by DHR category? Okay, because I don't have any Hilbert space ground state representation to do super selection theory with. But that's okay. We all know from DHR theory that there's that you don't really need the Hilbert space representation. You can use localized transportable endomorphisms. And that makes perfect sense for a net of algebras, but it's the wrong thing to do here. Because endomorphisms are too restrictive. These local algebras are not type 3 factors. They're finite dimensional C-star algebras. So if you insist on only using endomorphisms, it doesn't have nice structures of a category, and you're going to miss a lot of the stuff you should be seeing. So what you can do is reformulate the idea of DHR theory using bimodules. So you can have either, this is the category of DHR bimodules. And, you know, it's basically a straightforward adaptation of this localized. Once you understand the dictionary between endomorphisms and bimodules, which we know very well from subfactor theory, right? How endomorphisms give you bimodules, but bimodules are a bit more general when you're not in a type 3 von Neumann algebra. You can just translate localized transportable condition into kind of the existence of nice Pimsleur-Popa bases that are localized in various locations.
The channels?
You can't use channels, unfortunately.
Can or cannot?
Cannot. It's not enough. But what you can use, if you want to, is you can use amplomorphisms. So these are homomorphisms from B to a matrix amplification of B, but you have to require them to be non-unital if you want these to be fully general. So non-unital homomorphisms from B to amplomorphisms of B are actually equivalent to bimodules. And you can really write down an obvious definition of localized transportable in that setting. And it looks very similar to DHR. And you can prove it's a braided C-star tensor category. Yes.
But then everything that you get from this kind of assumption will be lost in the continuum limit, and in the continuum limit you only get the part that is DHR, or you
No, I think what happens is if you could actually formulate a continuum limit, these DHR bimodules could be represented as endomorphisms, because every endomorphism becomes a bimodule, yes. So I expect this to be invariant under renormalization. Like this is supposed to be a RG invariant sort of thing, like this DHRB. So if I did any renormalization flow I do should preserve this category. And so in some continuum limit, you would expect to see this as the DHR category, if you can make sense of it. Yes.
Yeah, I don't understand the starting point. So you fix any representation of G on.
Yeah, but it should be sufficiently nice. Let's just say the regular representation of G, so I don't have to tell you.
Yeah, because I'm thinking if you take irreducible, then
No, yeah. Well, no, irreducible could be fine as long as it tensor generates.
B becomes trivial or not. And
No. Because tensor powers of the irreducible representation can be or not irreducible. So the on-site algebra might be trivial if it's irreducible, but if I take tensor powers of this thing, or so if I look at an interval, it's in general not going to be irreducible unless it's invertible. Only if the representation is a character is every algebra going to be trivial. Yeah.
Yes, but okay, but your local algebras are tensor power of.
No. Local algebras are not tensor powers. They're fixed points of tensor powers, but they don't factorize themselves into tensor products. That's the key point with these symmetric subalgebras. Okay, one way you could think about what this is, it's very similar in subfactor theory.
Say the local algebra A is a tensor.
It is a tensor product, but B is not.
But the action is not just diagonal.
The action is diagonal, but the invariance, you can have,
Yeah.
Okay. The invariants don't factorize.
If you start with a regular representation, then itself is a UHF algebra.
It is UHF algebra, yes. Yes,
Not trivially.
Yes, but yeah, it's not bounded spread isomorphic to a tensor product UHF algebra though. And this DHR category is an invariant. It plays nicely with bounded spread isomorphism. So in particular, so I can tell you, actually there's examples of abstract fusions or abstract spin chains that arise in the situation of categorical symmetries that you can build. Basically, think about it, the standard invariant of a subfactor. What is it? It says these nets of finite dimensional algebras. Usually we think of it as indexed over N, but you can actually, if you do the tunnel, you think of it indexed over Z. Those give you great examples too. And those are the examples that appear when you do MPO symmetries. This is Yasu proved this in one of his papers. And there and so those also are great examples of this sort of thing. And in that case, the DHR category, what's it going to be? Does anyone have a guess? If I take a fusion category, say, and build one of these two-sided nets of algebras, just doing the standard subfactor stuff, what do you think the DHR category should be? The Drinfeld center of C. Okay, so that's a theorem you can prove. That is always the Drinfeld center. So in this particular case, this is actually a special case of that, because I'm just using the fusion category rep G, and my object is this object, and I'm just taking tensor powers of this object and its relative commutance of a subfactor. So it turns out in this case that if B is fixed points of AG, then DHR of B is equivalent to the Drinfeld center of rep G, or vec G, or whatever. Okay, so it's very similar to the orbifold construction, and it's the same story, right? If you took a holomorphic net and you had G acting and you took the orbifold, you would get some twisted double. In this case, it's an honest double. You take an honest action because the original net was like sufficiently trivial and it was an onside action. Okay, and now the whole point of this is when you do this DHR definition correctly, because you don't want to ask for things to be localizable in every interval, but just for every sufficiently large interval. And so that's where the main technical difference when you're proving this is a braided category is you have all these constants running around that you have to worry about. But the upshot is that this is actually, functorial with respect to bounded spread isomorphisms. So actually, if beta from B to B is a bounded spread isomorphism, then it induces naturally a braided autoequivalence on the DHR category. I'll call it DHR of alpha because I'm thinking of DHR itself as a functor. DHR beta is a braided autoequivalence. DHR, which in this group case, of course, is just the Drinfeld center of FG. And it contains finite depth circuits in the kernel.
Sorry, what is DHR of beta?
Yeah, so good. So basically, whenever I have any automorphism of an algebra, it induces an action on all the bimodules by just conjugating the left and right actions. Okay. It turns out if you have a bounded spread isomorphism and you take a DHR bimodule and you do that, you get another DHR bimodule. So actually conjugating in the category of all bimodules of this algebra B by bounded spread isomorphisms gives you a braided auto, and it turns out it's a braided autoequivalence of the DHR category. And so that's what DHR beta is the induced action that you get from conjugating by beta inside the category of all DHR bimodules.
Not be the Drinfeld center of vec G.
They're the same, but actually it's more natural.
Abelian.
What's that? No. For any finite group, center of rep G and vec G are equivalent.
They're the same.
Yeah, but rep G is the more natural one to use here, actually. But they're the same, yeah. And DHRB is trivial if beta is a finite depth quantum circuit. Okay, this gives you a nice invariant. So let's, before we move on, let's just think about what's going on in this Kramers-Wannier case. Actually, it's the same example that Matthew had in his previous talk, believe it or not. So what is the Drinfeld center? So what's the DHR category over here? Well, the group is Z2. So in the Kramers-Wannier case, DHR of the fixed points is rep Z2, which of course is the modular category, or sorry, it's the center of rep Z2, which is the modular category associated to the toric code. So there's 4 simple objects. They have Z2 cross Z2 fusion rules. They have 1 E, M, and F. And what is this braided autoequivalence? It's going to be the EM swap. Exactly the Kramers-Wannier case implements the EM swap, exactly the one that Matthew talked about. So if I think of this as 1 E, M, and F, then DHR of Kramers-Wannier equals EM swap. So there's a standard braided autoequivalence that switches E and M, it leaves one in F fixed, and that's the one you get from Kramers-Wannier. Okay, so you can kind of understand some categorical pictures about what are going on with this duality channel in this setting. Okay, so this is one invariant associated to a bounded spread isomorphism up to finite depth.
So like, if, oh, sorry. No.
No, so,
So if you start from the Ising CFT, and you do a deformation by adding this epsilon or whatever, like this, the dimension one
Yeah.
with the different signs, you flow, I guess, to these two limits that you've described.
That's right, and then the fact that this is actually it's a duality in the UV, but in the IR it becomes a symmetry, and that's why there's actually a symmetry of Ising CFT.
So I guess what I'm wondering is like, I mean, in the Ising CFT itself, you have like more symmetry, I guess, right?
Yeah.
You have the line, like the sigma line, which is, I guess, broken probably by the deformation, right?
Yes. You have more
But,
symmetry.
do you have access to that?
So in this microscopic model, you do not have access to that. You might have to pick a different microscopic model of the same universality class to access all the possible symmetries. Yeah. But in principle, you should. But there's a paper that's not written yet that does say you should. Actually, there was a paper that went on the archive just 2 days ago by Don Williamson and many co-authors, Lawrence Lutens and several people, that kind of show how to always build a microscopic model to implement any gauging map as a duality with MPOs. Okay. Okay, good. So here's one of my invariants, and here's an example of it. So you might ask, is this a complete invariant? Maybe this totally solves the problem. And the answer is no. There's something a bit more that you need. So let's see, what time am I going to?
Yeah.
To the 4? Yeah, it's hard for me to translate now. I mean, this is embarrassing. I grew up using clocks, but now it's hard for me to translate with the arrows meaning actual times. That's embarrassing to admit, but it's happened to me. So to the 4 is what I'll say. Yeah. I can do it, but it's not I need some error correction.
maybe one question about.
Yeah.
So I would have thought that the 1 EMF, they would those would correspond to some kind of generalized notion of DHR sector, and that the transformation, the Kramers, it would be like the symmetry that interchanges E with M.
Yeah, that's exactly right. That's what we're saying. So
Call it DHR.
What's that?
Call it DHR instead of.
No. Oh, sorry. Yeah. So DHR of beta. So DHR of the algebra is so this is an annoying thing. Apologies. In my paper, I set it up as DHR as a functor. So DHR maps an algebra to a braided tensor category, and it maps a bounded spread isomorphism to an equivalence. And so DHR is the name of the functor, which is an annoying thing. So DHR, so what this is, it says, okay, from an actual net of algebras with an actual bounded spread isomorphism, DHR of the algebra extracts the tensor category, and DHR of the bounded spread isomorphism extracts the symmetry. Yeah, so DHR of beta means what is the symmetry? DHR of the algebra is what's the category. It's just bad notation, maybe, unless you're a category theorist. Yeah, there's 2 different kinds of inputs because functors have 2 different kinds of inputs. Okay, good. So that's great. So that's one sort of thing. And I should mention, like like I said, this whole story works in this more general fusion categorical symmetry case. I just didn't want to go through fusion categorical symmetries because I thought this example was more visceral. People who maybe aren't as familiar with the fusion category internal symmetry. Okay, so there's another thing that you can do called the index. And this is a modification of what's called the GNVW index. This GNVW are Gross, Nesmet, Vaught, and Werner, I believe. I probably didn't pronounce the names correctly. But this is a really influential thing that is defined for genuine quantum cellular automata, which are bounded spread automorphisms of the big quasi-local algebra before you take the symmetric part. So in the case where there's no symmetry, this was introduced around 2010, and it gave a complete classification of QCA up to finite depth circuits. So in other words, if I pick B equals A, so B is the big algebra, then actually the DHR category is trivial, so this invariant is trivial. But this index that they wrote down is a complete invariant in that case. So the idea was, how can we generalize this GNVW index to this case of symmetric operators in a way that actually gives us an invariant? Maybe together those will be a complete invariant or something like that. So we were able to do that using actually Jones index for subfactors, or the C-star algebra version, but it's the same thing. So let me explain how this works. So what I'm going to do is I'm going to fix some point x. So here's my integers. I fix some point x, And so, and I'm going to define B greater than or equal to X as just the subalgebra of B, generated by X in BI, where I is greater than or equal to X. Like sorry, that may be ambiguous. I mean, I is over here. I just take all the stuff to the right of X, greater than or equal to in this partial order on Z. So B greater than or equal to X is just the subalgebra of B. Okay. And if I have a bounded spread isomorphism, so if beta is in QCA of B, what I can do is I can take beta and apply it to B greater than or equal to X. And I get some new algebra. Where is it localized? Well, it's kind of localized somewhere around here at the endpoint, where this R is the spread, right? But at some certain point, I contain all the other stuff that I had before. So if I pick some Y that's bigger than the spread, then actually this will contain B greater than or equal to Y, where really I can pick Y to be anything that's bigger than or equal to X plus R. So what I can do is, these are C-star algebras, but in this group case where you use the regular representation or is sufficiently nice, there's a unique trace, and if you want to, you can turn these into conclusions of hyperfinite 2-1 factors, and you can take the Jones index of that inclusion. Okay, so, or you could just use the Watatani index if you want to stay in C-star algebra, it doesn't matter. And so what you do is you define the index of beta to be equal to, you take the Jones index of beta of B greater than or equal to X over B greater than or equal to Y. And you divide by, you have to do a normalization because I'm just making some choices, X and Y randomly. So in order for things to not depend on the choice, I divide by the index of beta greater than or equal to X over beta greater than or equal to Y. Because the way I pick it, Y is already greater than or equal to X. It's just also greater than or equal to the image of the algebra containing this. And so I take this ratio of indices and I take the square root. I think, so this was a paper with my co-author, Junhui Lim. And I think he might have preferred a square root normalization, I forget. And you get this number called the index. And so what you can prove is that this is actually a homomorphism from QCAB to, what is this? Well, it's the multiplicative real numbers that we're using here, the multiplicative positive real numbers. And it contains finite depth circuits in the kernel.
It's rational?
No. Well, no. In this case of groups, it's going to be at worst quadratic. But in general fusion category land, it's just it's related to the dimensions of objects in the fusion category.
There were these papers by Friedman about QCAs.
Yeah.
Did you also use that?
Use this index for sure. Yeah. Anyone who does QCA stuff, this is like the fundamental tool in QCA land is this index. But I should mention the way it's originally defined is not with Jones index of subfactors. You look at these local algebras that are local, you kind of look at their image and you do some matrix algebra decomposition. That's only possible because everything's tensor product of matrix algebras. But it turns out you can do this instead, and it gives you the same answer as GMP. And when you restrict it to tensor product case. But yeah, this is like the fundamental tool for QCA. So we were like, okay, we need some version of this. And so the theorem is that in from QCA B to R greater than 0 times, so this is just a group of positive real numbers with multiplication, is a homomorphism. So it's multiplicative, and it doesn't depend on any of the choices. Homomorphism doesn't depend on X, Y, as long as they satisfy this nice large enough property with the spread, with finite depth quantum circuits in the kernel. So in other words, it gives me another invariant, or it gives me a homomorphism from this group that I'm actually interested in to the multiplicative real numbers. Okay. And so, yeah, so this does not have to be rational. As we know, Jones indices of subfactors do not have to be rational. And even in the group case, this doesn't have to be rational. It's because, I mean, well, in an obvious way, it's because there's a square root there. But this is the right the right thing to do to get to match up with the GMBW index. But in the general fusion category case, it can be all kinds of numbers. So what's the upshot? So now I have a pair of homomorphisms in cross DHR. Again, using this funny, weird way of DHR as a functor, as a homomorph. I'm calling basically the homomorphism from here to here. I'm calling that DHR, which is probably confusing. But this goes from QCA mod finite depth quantum circuits to what does it go to? So it goes to R greater than 0 cross times braided autoequivalence of center. So it goes from here to R cross braided autoequivalences. And okay, I'll just say in the group case, because that's how I set everything up. So it's a Z of rep G. Okay. So the theorem is that this is injective for the group case with the regular representation, and some other cases that we know of too.
Super question. I'm not sure, not really on all this stuff here, but in this index case, you said that there was a formula in terms of quantum dimensions. So in the group like case, is this in terms of dimensions of rep G?
Yeah, exactly. But then there's a square root.
Is it a simple formula?
It depends on the bounded spread automorphism, right? So it depends on how complicated the bounded spread automorphism that you handed me is.
So for example, the one you started with
This will be square root of 2,
just square root of 2.
which is not coincidentally the dimension of yeah, exactly, of the symmetry in the IR.
So if you have a Tambari Yamagami, is that always the
Yeah, it'll be a square of the row. If you pick a standard, so I'll give an example at the end with Tambari Yamagami. Yeah. And then yes, it will be a dimension. But in general, it could be like ratios of dimensions. It just depends on how you build it. Okay, good. So yeah, so the theorem, and this is a result with Dominic Williamson. But let me get the names in order, I guess. My student Kylan Schatz and Dominic Williamson, who's a real physicist. I'm just pretend, but Dom's a real physicist. So theorem, this is injective. And I can actually tell you what the image is too, but it's kind of complicated to write down. But this is injective for regular representation. So for G acting on L2 of G. Okay, it's a finite group. L2 of G maybe is overkill. And so that means that if you give me a bounded spread, if you give me 2 bounded spread isomorphisms of this symmetric subalgebra 2 QCA, and you want to tell me, do they differ by a finite depth circuit? Are they in the same coset up to under finite depth circuits? If you compute its index and you compute the way it acts on the DHR category, and you compare those 2 things, that will give you an if and only if answer. Okay. This result itself doesn't tell you, it would be nice, what's the actual group structure here? And it's a little bit weird. It's an extension of one thing by another thing. I can tell you, what the elements in the image are. But yeah, we haven't found a nice way to say what the actual group structure looks like. But nevertheless, if you're thinking of this as like an invariant tool to tell whether or not these 2 things are apart, this says this numerical index generalizing GMVW and this action on the DHR bimodules, they tell you everything you need to know. Okay. So how general is this? I don't know. But my conjecture is that if you take any integral fusion category and you use the regular object in that category, which is just the object, and then each simple object, you take that simple object with multiplicity corresponding to its quantum dimension, which is an integer, and you take the direct sum of those. Then if you build your spin chain with that thing, your abstract net of algebras with that thing, then I think that this will always be injective. Okay. So yeah, so now let me give you some examples. So we have Kramers-Wannier already, and in that case, I should say, yeah, in the Kramers-Wannier, is square root of 2. So let me give you a nice generalization of Kramers-Wannier that's very much related to Tambari Yamagami categories. And in this case, I'll choose my group G to be abelian. And take some, let's C be a TY G Tambari-Yamagami category. So there are, these are classified by non-degenerate bicharacters on G, symmetric non-degenerate bicharacters plus a choice of a sign, but I don't care which one, just pick any one and call it C. Okay, so C will have some object rho that satisfies rho tensor rho, is isomorphic to the direct sum over all the group elements. Right, Tambari-Yamagami. Okay, maybe some of you don't know what this is, so let me actually say what this is. The simple objects in Tambari-Yamagami are given by G, and then one special non-invertible object rho, and rho has this fusion rule. So if I tensor rho with itself, it's the sum over all the group elements. Rho times G is just rho. So rho kind of absorbs the action by G, and then when I tensor product the G together, I just do the group multiple. Okay, so take this. So notice so here's what you do. So build a fusion category net with C. So with one of these non-group theoretical fusion categories, this thing, the quantum dimension of this is the square root of the size of G. So in general, this does not look like representations of a group or a Hopf algebra. So build a fusion category net with C and rho. Okay, which means that, you know, I'll define my B sub I to just be endomorphisms in the fusion category C of rho to the tensor I. So what that means is that basically I just take, right, if I has like 4 points, I just take Homs from rho, rho, rho to rho, rho, rho. And if this is my interval I, and then I just add in strings everywhere. And this is the usual subfactor thing, right? This is just from maybe say you could take the even part of a group subfactor, group type subfactor, okay. And you get this big net. But the thing to notice is that if I chunk rho and rho together, rho tensor rho is the sum over all the group elements. So I can think of that as being an object in vec G, and since G is abelian, I can use my bicharacter to make an isomorphism of that with rep G. So really, if I think of G as kind of like the dual group of something else, then this object is the regular object in rep G hat, in other words. So rho tensor rho, if I think of vec G as actually equivalent to rep G hat, where G hat's just the dual group, then rho tensor rho is the regular rep of G hat. So if I coarse grain this net of algebras by just blocking these rows together, I actually get the thing I was interested in, which is you take the regular representation of the group G, but now I'm doing it for the group G hat. So I'm using G hat as my thing. So I have G hat acting on site in the regular representation. I take that net of algebras. It's actually isomorphic to this net of algebras once I coarse grain, once I block the rows together. Okay, but the advantage of doing this now is now that I have this secret factorization into rho tensor rho, I can just shift by one row, right? So I just shift it over by one. I shift everything over by one. And so, you know, if I'm thinking of this as just a regular representation at each site, you know, if I block it together and I didn't know I had this factorization, that would look like a weird isomorphism because you don't see the rho tensor rho factorization inside rep G hat. You only see that outside in Tambari-Yamagami. But you go outside, you do this little shift. It looks like some weird thing if you just knew about the rep G net, but that would be bounded spread isomorphism. And in fact, Kramers-Wannier is exactly this for Z2. Like this is one way you can write down Kramers-Wannier is literally this form. Okay. And so what you get, what the automorphism on the center here is the standard electric magnetic duality defined by the non-degenerate bicharacter that you used when you picked your Tambari-Yamagami category. And the index in this sense will be the square root of the size of G.
Can you say again what's beta? I missed that.
Beta, yeah, so beta is shift by one.
By one row.
By one site. So I take an operator here and I send it to the operator there.
Row side.
Yeah, by one row site. Which, like, because it's an isomorphism of algebras, gives me some bounded spread isomorphism, but it looks super funny if you tried to write it down in the rep G hat language. It looks like a guy like that Kramers-Wannier thing did. And so the invariants here are what you expect. It's from a physics perspective, the action on DHR is the electromagnetic duality defined by the bicharacter, and the index is just the dimension of this row object. Okay, and you can imagine an easy generalization. You could take any Zn graded extension of your fusion category and play the same game where you block it according to the size of row. And anyway, there's a generalization, and in fact, there's a theorem in the works that essentially all bounded spread isomorphisms look like this in some sense. There's some secret factorization in a larger thing, and you're just doing a shift in that secret factorization. So that's kind of a theorem in the works. Is that everything's going to look like that, and from that you can compute the indices and all that stuff. So I'll end there. Thank you.